Hello everyone. So previously we learned analysis of variance, but it was for one-way classification. So we had one factor only. So today we will learn about if we have two factors. Let me go in there. Show you here. Okay. So I would like to start from here. So whenever we have two factors, that means we have two-way classification. And then between those factors, we also have some interaction. So you can also read about if we do not have any interaction between those two factors, how it affects. That means we don't have any interaction effect. You can read about that. But I would basically like to show you an example where we have two-way classification with interaction. So that means we have three kinds of species. And then you can see that in each of those species, we also have information of the fertilization, that means the treatments. So you can see the controlled versus two treatments. And then each of them, so let's say within FAR species, whenever we have control, then you can see that we actually take the replication. That means we try to do the same thing on 4 of those observation. That means each treatment, the FAR, and then you can see that we have the control group. Each treatment is actually replicated on 4 plots. And then the information we get, we are trying to get the height information. So one error in here is that whenever we try to find the total, so you can see that we calculated 3 plus 3 plus 0.3 and then all these 4 values. So we sum them, we find the sum 12.8, but the last one, you can see that it should be 15.2. I'm not correcting in here. I will show you in the Excel file because all this needs to be fixed. So I'll show you in the Excel file how what should be the mean and what should be the total. Okay. So in this case, we have the sum of squares is coming from 4 different cases. So you can see that we have the sum of squares for the treatment, for the species, and then for the interaction. That means whenever we have treatment and species, so you can see that we have FAR and then control, or FAR and then fertilization 1, fertilization 2. So that means we have some interaction going on. There should be some effect. There should be some sum of square for those interaction. And then we also have the between siblings interaction. We also have interaction between two factors, the species and treatment. Similarly, what we did before, we will also try to find the sum of the squares. So I will show you all these equations, how I found that. And then in our cases, the hypothesis we have is whether the treatment means, that means we have 3 treatments, whether they are same or not. And we have another hypothesis is that whether the species, for each of those species, the average we will get for the height for those siblings, whether they are same or not. That means I said in the null hypothesis they are same. Similarly, for the interaction, when one of them is present, then another will be affected. That means treatment will be affected by species. So we say that the interaction between them, whether they are actually same or not. That means the null hypothesis, we say that they are same. Alternative hypothesis, similarly, it's the at least 2 of those means that we see in here are not equal. And then 2 of those means for the species are not equal, and then 2 of those the differences of the interaction we found, they are not equal. Okay, so analysis of variance, we will also try to find similar table that we saw in one-way analysis of variance. Let me show you over there. So two-way analysis of variance, you will see that they are a little bit lengthier. Just like me, if you can identify all the means, sum, and then identify all of them at the beginning, then it will be easier for you. So I showed you the hypothesis, and then at first let me describe what I would like to do. So you can see that I mentioned how many treatments we have. We have 3 treatments, 3 species. So I define them by K, T, and the number of observation in each replicate. That means how many observations we have in each of them. So in each of those cases, you can see that we have the same number of observation. That means it will be 4. That's what I try to define. And then I use the subscript IJL. So I is for treatment 1 up to 3, and then J is for species 1 up to 3, and then L is for observation 1 up to 4. And then this is actually what we saw in the data set. We have species and we have fertilization, or you can say these are treatments. At first what I did is that I tried to see how many samples in each of those columns, and then I tried to sum all these 4 values. So you can say I found the sum. This sum is actually the Tij dot, because we have the treatment, we have the fertilization here, and then we have the species far. So that means this is fixed, and then only thing is varying is the replication. So that means that's why this is Tij dot. And then I try to find sum of these 4 values. After I find sum of these 4 values, you can see that that's the only difference in the lesson. Also in the textbook you will see that this is 15.8, but it should be 15.2. And then you can see that I actually sum all of those sum. When I sum them, this is the grand total. That means the T dot dot triple dot is the sum of all of them is 126.2. So that's the grand total. We can also find for each observation if we take square of them and sum them. So you can see that I squared them, each of them, and then sorry, I actually squared this one. The square the sum, that means the Tij dot square, that means each of those I take the square and then sum, and then try to find the sum. So that means the only replication is actually varying in here. That's why I wrote down, if I have Tij dot square, that means the replication is only changing, and how I can find that. So let me define again. This one is actually square of the total. That means if I find the total of those 4 values, then I can find the square of them, and then I sum them so that I can find Tij dot square. This one is you used before, so in each of those values you have to take the square and then sum them. So you can see I squared 3.3, I squared them, and then these 4 values I squared them and then add them. And then if you add them all, then you will see that this is 451.8. This is actually square of each of those values, then sum them. Okay, so be careful when you do that. And then these are optional, you can find them or not. So I try to find for each of those columns what is the variance and what is the mean. Okay, so after that, so I try to find what's the value for K multiplied by T multiplied by N, because I need to use that in this equation, because few of them I try to calculate earlier, because this value, the grand total what we found in here, so grand total I will be using it for many times. So CF is the correction factor, so you can see that CF is the grand total square divided by all these KTN. That means 3 multiplied by 3 multiplied by 4. So I divided 126.2 square divided by these 3 values, and I found this the value. So I will use it in all of those sum of squares. So you can see that we have to find the sum of squares of total, and then sum of squares of total is really simple. What you found the square of each of those values in your data table, if you take the square of them, each of those values, and sum them, then you will find that this is the value. That's what I described before. And then at first I added that minus this correction factor. So that's what I did, the sum of them and then minus the correction factor. So that's the total sum of square. For species, if you need to find the sum of square, then you have to use this formula. That means for species, all we need to do is to take a look at where we have far. So you can see that far we have here. So that means if you sum these 12 values, then you will see that you will get 45.2. Or you can just sum these and you will find that for far, for hemlock, for cedar. So that means in your data, what's the sum for them? Hemlock, sum all these values. Cedar, sum all these values. That's what I did. And this is, since this is the species, that means J is changing, J is fixed, and then everything else is changing. That's why I say this is D dot J dot. You can give any other symbol. And then I squared them, each of those, and then sum them. That's what we need in the species sum of square. So that means square them and then sum them. So I found the value divided by k and n. So that means you can use the k, n is 3 and 4. So that's what I did for the SSB. I named them as SSB. So I say that sum of squares of them, minus divided by k and n, and then minus the correction factor. Similarly, I did for fertilization. So you can see wherever I have control group, I need to find the sum of them. So you can see control group is here, here, and here. So that means you have to sum these values. Similarly, for F1 fertilization, you have to find wherever we have F1 and you have to sum them. So that's what I found in the sum. And then I took the square of them. After I took the square of them, then I summed them. Similarly, what I did is that was the sum of squares of some of them I found, minus, divided by t and n, and then minus the correction factor. So I wrote minus twice, it should be 1 minus only. Okay. And then for the interaction, you have to do a little bit of more calculation, but we already found all these values. So you can see that this is the Tij dot square. That's what we found already in here. That means whenever we took the squares of those sum, then we found them. And then this is 1802. So you can add that value, and then SSA, SSB, you already found them for the fertilization and treatment, or treatment and the species. And then you also found the interaction. So that means you have to add all of them. Sorry, I was talking about SSB. So in SSB, you have to add what you found before. So I showed that, divided by n. That means each replication is 4 times, minus the correction factor, and then SSA, SSB. Similarly, you can see that what's the total sum of square minus SSA, SSB, and then interaction. Then you will find that that's the error sum of square. Okay. If you find that, you will see that if you find the interaction, SSA, SSB, and total, then the rest is easier. So all I did is that for two-way ANOVA, this is the ANOVA table. So in this ANOVA table, I said what are the sources of variation. Sources of variation are factor A, factor B, and then interaction and the errors. Degrees of freedom is similar to what we have in the data set. So you can see that in the factor A, we are saying that this is the treatment. So that means for treatment, we have the k number of treatment. So this is k minus 1. Factor B is the species, t minus 1. And then interaction is the multiplication of these two. And then error is the kt n minus 1, that's what you can use, and then the total is the kt n minus 1. And the mean squared error, previously I showed you in one way ANOVA. What we did is that if we take the sum of square divided by the degrees of freedom, you will get the mean squared for all of them. But for computed f, that means the f statistic would be mean squared in the factor a divided by mean squared in the error. That's what you have to use for the other ones. And critical values will follow what you used in the denominator and the numerator. In the numerator we use k minus 1. In the denominator we used, for all of them, we use kt n minus 1. So that's what you have to use for finding the f critical value. The rest is simple, so you only need to add the values you used in the this table k minus 1. That means we have k is 3, 3 minus 1, 3 minus 1, and then 2 multiplied by 2, because k minus 1, t minus 1, you have to multiply that. And similarly you can find the other one. Sum of squares we found before, so what's the sum of square of each of them? You can add them, and then you can see that I found the mean squared and then computed f. The values, I say that because of one value everything else change. So you can see that I found the critical values. At first we need to find what is the interaction critical value and then the statistics value. So we find that the interaction is actually exist. That means we are rejecting the null hypothesis for the interaction. In that case we will stop here, because whenever we find the interaction present, then if we're trying to interpret the factors itself, that since they are actually linked with each other, they are interacted. That's what we found in the hypothesis testing. Then they are actually related. That means we will stop in the interaction. If we need to find the confidence interval, similarly, let's say I want to find the confidence interval for treatment means. So all you need to do is that you need to find the standard error, the t-value, and then what's the mean. So let's say I'm talking about the mean for treatment C. So where is the treatment C? Let's see. So for the treatment C, you need to find the mean for treatment C. So let's say, just for example, let's say I found the mean. It is the sum divided by 12, so that I can find mean. So I found mean for the treatment C, and then the standard error for that treatment is the mean squared error that we found on the ANOVA table. Mean squared error divided by t and n, because these two are varying. So you can add those t and n. So you can say I added those t and n. T and n I found from before, and then I found the standard error. Then I found the t-value. So we need to look for, let's say, 0.975, but you can see 0.25 or 0.975 will give me the same value. But in the t table you need to find it for 0.975, because 0.025 doesn't exist. So let's say 0.975, and then 27 is the degrees of freedom, because you can see the degrees of freedom we said kt n minus 1. That means what we have in the error degrees of freedom, that's what I used. So I found that this is the t-value, and then just the mean minus the standard error of mean multiplied by the t-value. I found the lower limit, and the upper limit you have to add the multiplication of these two. So that's how I found the confidence interval. So that's about the two-way classification with interaction. If there is no interaction, if you find that, then you can actually do the calculation that we showed in here. That means you can omit the interaction for the for those two factors. So you can see that that's the same thing I showed you in the Excel example, and you can see that if there is no interaction, then treatments are different. And then if there is any interaction, then we cannot say whether the factors are varying or not. We have to interpret the interaction. And then you can find the confidence interval similarly, the one I showed you. So that's it about the analysis of variance for two-way. That means two factors we have. Thank you.